Hello and welcome to the lecture Neural Network Fundamentals. Today we'll discuss overfitting. In this lecture, we are first introduce the concept of overfitting. Then we try to understand what we mean by bias and variance, bias-variance trade-off, and then different solution of overfitting. For example, k-fold cross validation, regularization, or distortion, etc. Okay. Today, we are going to start a very important concept called overfitting. So, a overfitting is a situation when a hypothesis function is be overfit if there exists another hypothesis function H bar with higher training error but lower testing error, indicating that H generalized poorly to function. Now consider our linear regression problem where there is a hypothesis function H that we hypothesize for a given training data. Now, the overfitting is basically a kind of situation when there exists another hypothesis function for if that is our first function is h, another is h bar, let's say. And for h bar, training error is higher than the h, but testing error is lower than the h. If this kind of situation happens, we say that our actual function h is generalized poorly to nonce data. We'll see in this lecture that what actually is happening and what does this sentence means or what is mean by generalization and so on. So a classifier that perfectly classifies the training data may not generalize well. It is one thing we have to understand very well. In general, this is a common mistake we have done, that we always try to minimize the training error. But the performance of a classifier may not be evaluated through the training error performance or training data performance, its performance of training data. Rather, its performance is basically evaluated how well it performs on the testing data. Okay. So training data may contain noise, causing the model to learn irrelevant patterns. Now, the situation why this happens may sometimes training data may have some noise, and if our classifier is very keen to the training data, it generally learn this noise also. This is not actually a pattern, rather an outlier, but it also learns or memorizes. It another time it's happened very frequently when training dataset be very small, making an unrepresentative of the true characteristic. That time also it happened. So if we say simplistically, a model, when model is too complex, that there is a tendency of overfitting, and the model, when it is too simple, it a tendency of underfitting. What underfitting means will also come, and it can't model the training data well also. So one thing we understand here, the training error is not a good predictor for the testing error. That means if your classifier is performing very well on the training data, it may not be going to perform similarly or similarly well for the testing data. Now, when we go a bit deeper. Let D represent the entire data distributions and T represent the training set or training data set. Now, hypothetically say that this hypothesis function H belongs to this hypothesis H is said to overfit when there exists another hypothesis H bar that is not H, okay, it's other than H, such that H achieves a lower training error. That means training error is lower for H than the H bar, but higher training error overall data distribution. And now overall data distribution we don't have, so there is a representative data distribution for actual data distribution is called testing data distribution. So test error or overall data distribution is higher H than H. In other words, the model performs exceptionally well on the training data, but fails to generalize to nuance in example. If this situation happens, we say that our model is overfitted. Definitely, when we training a model, our one objective to minimize the training error, and that is important also for learning pattern in the data. But our primary objective is to achieve a low generalization error. That means that our model not only perform well to the training data, but also that performs or their capability reflects on the entire data distribution. So generalization means that it learn in general the actual data distribution, that is D. So since the true data distribution D is unknown, we estimate the generalization error using a separate test dataset that was not used in training. That we have said just representative of our actual data distribution or the test dataset. Therefore, test error served as an estimate of the model generalization error. And what we require? We require this error low to ultimate goal of the machine learning, because it indicates that the model can make accurate prediction on unseen data rather than merely memorizing the prediction set. So this is as a whole the problem of overfitting. Now we try to understand the problem of overfitting in a bit different angle. So what we have said, overfitting occurs when a machine learning model learns the training data too closely, capturing not only the underlying patterns but also the noise and irrelevant details. As a result, it performs well on training data but fails to generalize the unseen data. That we have said earlier. Now, here you see that this is the case. So these are the data points and this is the line. Now, one thing we try to understand the model complexity associated with this particular model is very less because it's linear in nature. It's a very less complex model, very simple model, and it fails to capture the points or the data points very well. So it definitely not performing well for the training data. Rather, there is some curve. That curve is not that much good, but it more or less better than this straight line. So somewhat well. Now you see the data in this case. Now this is a very complex curve. This curve is not that much complex. But here it's a very complex curve, and it essentially touches upon all the points. So the model complexity here is too high. It is medium and it is medium. So if model complexity is too high, it has a nature that it tries to memorize all the points. Now the question is, if this point you think, this point may be outlier, this point, this is outlier. So these curves are basically ignoring this. Rather, this is a kind of distribution. Hypothetical. But this curve also considers. And that is the pitfall, that is the problem of this very highly complex model that essentially take care of all the points. But actually, it not generalize that actual distribution. So a model with too many features or excess complexity may fit the training data extremely well, yet perform poorly on new examples because it has memorized the training set instead of learning generalizable. So that is the major, and this is called. Now here, a similar problem for classification task. This is a very simple that is not good even for this data points, but it was somewhat balanced. That is well fit, but it is a very complex curve and negative. So this is as a whole a very visual illustration for problem. Now, the problem of overfitting can be explained through this kind of flowchart like representation. Let there is our model. If the model performs well on test data, if it is yes, then it's a good model. Please note it is a test data. So if it performs well on test data, it generalizes well on the distribution. If no, then we question it. The model performed well on training data. If it is also no, then definitely the model is performed not well test data as well as the training data, so it's underfitted. But if it perform well on training data, but it is perform not well on test data, there is a chance of overfitting. So overfitting, the problem of overfitting can be viewed in this by this flowchart like that. Now, one a very interesting question here. Why data overfitting considered the most common pitfall in why we commonly make mistakes so that our model become overfitted. One, some human tendency may be a reason. For the example kind of, and then train and test data set. When I said train test split, we generally use the most of the data for training. Very less data or little bit small number of test data are used for testing. So that is one of the reasons that this overfitting may become an frequent issue. Another very kind of human tendency is that we always like to choose a complex hypothesis. So we are a bit inclined to the high model complexity. Why? We assume that larger model always perform better because they fit the training data more closely. Our major concern, the major attention is on how we can get a good result on training data. But we forget about one basic assumption of the machine learning, that performance of the model doesn't only depend on the how it behaves on the training data. Mainly, it depends how it perform on the testing data. So this is the one another reason that we frequently encounter overfitting problem. Finally, it is often difficult to realize that a model performing well on the training data may still fail on the unseen test. This is a kind of human, you can say, mindset, that we realize that model is doing well on the training data. It should do well on the test data, but it may not always the case. So it's why this kind of, it's most of the cases, mainly for very challenging situations. Achieving high training accuracy is already bit tough. And we often focus only on fitting the training data and overlook the model's ability to generalize. So these are the some reasons that generally overfitting become a very important problem, a very frequent problem, modeling of machine learning for computer vision problems. Now, again, we try to understand this problem from another two very important terms. One is called bias, and another is called variance. First, we have to understand what is bias and what is variance. Now, bias is the error caused by incorrect or overly simplistic assumption made by a machine learning model. Let's say our model is very simple. We can go back here. Our model is very simple. It's just a straight line, a very linear model. But becoming a very simpler, this particular model cannot represent the data points or here the decision boundary. So that means there a chance of underfitting. So this is called the bias. It represents the difference between model's predicted output and actual predicted output. A model with high bias are generally too simple. That means that in our example, what is to capture the underlying patterns in the training data and resulting under. So high bias means extremely simple hypothesis function or decision boundary, so that it often failed to capture the underlying patterns of the training data and causing underfitting. High bias typically leads to high error in both the training data and test data. That is very easy to understand, because if model is very simple and it fails to capture the training data or model training data, definitely it will be doing poor at testing. So this is called bias. On the other hand, variance is the error caused by a model being too sensitive to the training. Now, what if a model is very complex and it very accurate for the training data? So models with high variance are generally very complex and learn the training data two groups. Even it learn the noisy training samples. And this kind of nature reduce their ability to generalize to others. This kind of situation, when our model is too complex or the number of training samples are too small, then there is a chance that model a very high variance. Sometimes it's memorizing, and this results overfitting. While model perform exceptionally well on the training data, but poorly on nuance in data. So high variance typically leads to very low training error, but high testing error. And high variance is basically the cause of overfitting. Let's try to understand the same situations or similar situation is bias variance using a bullseye diagram. Now it's a low bias, low variance case, and definitely it's the ideal case. Predictions are closely clustered around the true target and bullseye, and indicating both high accuracy, low bias, and high consistency, low variance. And that is ideal because that we really want. This represents an ideal model that generalizes well to answer. So this is the ideal case. Next comes the high bias, low variance. Now high bias means what? It is not captured the training samples well. Predictions are tightly clustered but far from the true target. Why tightly clustered? Because of low variance, but it actually don't cluster the underlying distribution. So it is basically causing underfitting. The model is too simple to capture the underlying patterns in the data, resulting in high training error and high testing error. And this is called underfitting. Next thing is that low bias, high variance. Now low bias means that predictions are centered around the bullseye. It is centered, but are widely scattered. See, these data points are widely scattered. The model is overly complex. It's very much model complexity is very high, and it fit training data very well. Even it model the noisy data samples for the training samples, resulting in very low training error but high testing error. So it loses the generalization. So leading a poor generalization, and this is called. So overfitting, low bias, high variance is important to remember. And finally, high bias and high variance is both the bad situation, the poor situation. Predictions are widely scattered and far from the true target. The model is both inaccurate, high bias, and inconsistent, high variance, resulting in poor performance in both training and testing. That would be very important. So this is the way of understanding dimensions of bias and variance, what we mean by overfitting and what we mean by overfitting. Now, what we basically try to understand, there is a trade-off between bias and variance to get our ideal model. So why there is a bias variance trade-off? First, you have to understand this. Now, before we explain, we try to understand this diagram. Now, this bias curve is actually bias square curve, is this red curve. With model complexity, bias is basically decreasing. It's very easy to understand because in the left, in this side, model complexity is simple, and when it is going complex, definitely the bias will be reduced. That means model capture the training data. On the other hand, if model complexity is too simple, variance is low, and with higher model complexity, variance are increasing. The question is that where is the best zone or best for our ideal model? So here you can say that here these two curves intersect, and this green dotted lines, these zones, is the base zone or solution zone, which is the total error, and basically, and this total error is basically bias square plus variance and some irreducible error, some issues. So this particular chain give a idea that which model complexity we should retain our model so that we can get not the very bias or not high bias, not low bias, or variance also is not that much high. So not high bias, not high variance. So it is a very kind of ideal zone for that. So this is the meaning of this particular figure. Now we read out this uh, understanding and to understand how actually these figures tells us that how we choose bias and variance in keeping in the mind the trade-off between these bias. So a model with high bias and low variance is too simple and has a fewer parameters to complexity. Such models may go to the or may lead to the underfitting. That also we have seen in the previous slides. Now a model with low bias and high variance is highly complex and has a large number of parameters. Such model basically fit the training data too closely, including its noise, and may lead to the overfitting and generally have poor generalization. So here where we find this is high bias, that is also good. This underfitting area. High variance, that is also not good. That is for overfitting. So the model complexity increases, bias decreases, that you can see, but the variance increases. So conversely, reducing model complexity increases bias but reduces variance. That is very evident from this picture. Therefore, a trade-off exists between bias and variance. So how to choose this bias and variance? And the goal or objective is to choose a model that achieves a good balance. So this is the balance shown with low bias and low variance so that it generalizes well, avoiding the productivity. That from these definitions or the statements are very much understandable from this figure. So for our for the good model, find a good balance between bias and variance and minimize the total error. So this is the total error, this curve. And this is bias square plus variance, reducible error. So optimal balance and bias and variance would never overfit. So this is basically called the bias variance trade-off. So by these different kind of representations, we understand that how overfitting occurs and how is underfitting occurs. and how we choose the model complexity to avoid both of them. Okay. Now we are going to understand what are the solutions if overfitting occurs, or to prevent overfitting, what we can do. So three different solutions we're going to discuss here: k-fold cost validation, regularization, and early stopping. Now, first of all, what is k-fold cost validation? Now, as we know that there is a two split, one is training set, one is testing set. Training set may be again divided training set and validation set. So here the basic process is that we divide this training set with k number of different subset. That is the, we divide it. Now we first define what is k-fold cross validation. That it's a technique used to evaluate models' ability to generalize to unseen data and reduce the risk of it. So it's kind of precautionary measure, you can say. So instead of training and testing the model only once, the dataset is divided at k equal folds. Dataset means training dataset. That is basically k equal folds. And the model is trained and tested k times. Okay, using a different fold as a test set in the registration. So if you round 1, training set is S minus S1 and validation set is S1. Round 2, the training set is S minus S2 and so S minus S1 means what? S2, S3, S dot Sk. And similarly here also you can see S minus S2. So if you say the step-by-step procedure, choose a value of k, common choice maybe 5 or 10, split the data sheet in k folds as we said. For each fold, train k minus 1 folds, train on fold, test on the remaining fold, record the score acquisition as, and for all this k minus all these k folds and compute the average. Okay, so this way we have. The question is why it helps. So k-fold cross-validation improves the model's ability to generalize by providing a more reliable estimate of its performance on unseen data and reducing the risk of overfitting during selection. That we have just as a definition, but why? Now, what is happening here? Unlike a single trend test split, k-fold cross-validation evaluates the model across k different validations. So k times it is trained and testing on k different validation set, ensuring that each data point used once validation and k minus 1 times for train. So what is happening? Because since it is so many times trained on a different data set and testing on a different data set, it reduces the dependence on a single data set, which allows the model to learn for a broader representation and produces a more accurate assessment of its true predictive performance. So underlying distribution, it learns very well. What does this mean? The generalization power is increased. Additionally, averaging the result across multiple folds gives the variance associated with several characteristics, minimizing the influence of unrepresentative samples and yield the more stable and on that starts to evaluation. So that is also true because many times it basically we take the result and sum it up and average it. So this unwanted samples are averaged out. So in overall study, we define careful cross-validation as the generalization by requiring the model to perform consistently well across the multiple unseen subsets rather than excelling on just one particular split. And that is the basic idea. Why careful cross-validation helps the generalization. Next comes regularization is another technique. Regularization helps the model to generalize better on concept data. What is basically do? It penalizes the model complexity. During training, regularization adds a penalty term to the loss function, discouraging the model from becoming overly complex, and it helps to prevent large weight values using too many features, learning highly complex or overly flexible models. So, in regularization, is trying to do that we want to get a very accurate performance, but it also generalizes well by reducing some features or make the model as much as possible simple. So the loss function of regularization is the original loss plus lambda into penalty. Lambda is the regularization parameter which controls the strength of regularization. Larger lambda means simpler model, smaller lambda means more complex or flexible model. Now there are two types of basic regularization. Regularization reduces the overfitting, adding penalty that we have said cost function. This penalty encourages the model to learn smaller weight values in a simpler model to lower complexity and better. So generally two types of regularization we find is lasso and this ridge. In lasso, there's absolute values of the coefficient is like this with this original loss function as a penalty. It focuses some unimportant ways to exactly zero. So it's basically feature selection. Remove some unimportant features, reducing the model complexity and improving information. On the other hand, reach adds the squared values of the coefficient as a penalty term as function. This causes large weights to decay but does not force them to become zero, allowing all features to contribute while spreading the influence across them, which is important feature contribute more, which is unimportant feature is contribution is less. So it is the squared. Now finally, another thing that is called early stopping. Early stopping is a regularization technique used during the training of the models with iterative optimization methods or gradient descent. So this method updates the model parameter in each iteration and improves its fit to the training data. How? Initially, each iteration improves the model's performance and based validation. And beyond certain points, you can see here, this is a early stopping point. This is accuracy. It start decreasing, so we stop here. Or it is from the early stopping point. It is the overfitting. This is test set and training set. So loss is start increasing. So we stop it here. Beyond a certain point, further fitting the running data increase the generalization error due to overfitting. So we stop there. Early stopping holds the training at the optimal solution before overfitting begins. And efficient. So these are the very main way to solve this or prevent. So in this lecture, what we have considered that concept of overfitting, then what we mean by bias and variance, and explain underfitting and overfitting by means of bias and variance. Once you understand what we mean by bias variance, then we try to understand a different solution to the overfitting, careful cross validation, regularization stuff. In the next lecture, we start our convolution of the overfitting. Thank you very much.